Swayam Prabha. Digital India. Educated India.
Hello and welcome to Lecture 8 on Special Relativity. In today's class, we will continue our discussion of spacetime diagrams, and we will see how we can intuitively understand the ideas of length contraction, time dilation, and the relativity of simultaneity from these spacetime diagrams. And then we'll discuss the important ideas of time ordering of events in special relativity as seen by different inertial observers, and the relationship between time ordering and causality, that is, the ordering between cause and effect. In today's class, we'll try to understand spacetime diagrams and how they translate from the observations seen by one inertial observer in a frame S to the observations seen by a different inertial observer in a frame S prime. So here I've shown the spacetime diagram for an observer in a frame S, and their origin will mark as 0, 0, 0 in space and 0 in time. And one way we can locate the x-axis, that is the points which are all at t is equal to 0, is to identify where we have t is equal to 0 and take all corresponding x values or spatial positions. Okay, so this defines our x-axis. And similarly, we can define the position where x is equal to 0 and take all possible time values, and that defines our y-axis of the spacetime diagram. Now, let's imagine that we have a second observer in a frame S prime who is moving with respect to frame S with a speed v along the x-axis. So, of course, our special relativity transformations tell us that, we'll write this down. So, if we measure the time t prime as seen by observer S prime, or rather Ct prime, that would be equal to gamma times t, or Ct, minus beta times x, and x prime would be gamma times x minus beta times Ct. Okay, and y prime would be y and z prime would be z, and we're not representing them here in our spacetime diagram. Okay, so you can think of this spacetime diagram as valid for a particular point. Let's say y is 0, z is 0, or for any other y and z, you would get exactly the same spacetime diagram. Okay, or at least the transformation between observers S and S prime would look the same at any other point y and z, and the corresponding y prime and z prime. Now, one important choice that we've made here is that we have taken the origin, that is t prime is 0, x prime is 0, in the frame S prime, to be the same as the spacetime point t is 0, x is 0, as seen in the frame S. So now when we say we want to understand what the spacetime diagram would look like to an observer in frame S prime, what we're saying is that if we identify a particular point in spacetime as seen by observer S, which has labels Ct, x, okay, which locate the time and spatial coordinate of this event, we would like to know what the labels are of the same spacetime point as seen by a different observer in frame S prime. Now, of course, we know mathematically how to relabel this point using our transformation equations, but what we would like to do is figure out a pictorial or graphical way in which we can figure out what the coordinates of this point would transform to according to the observer S prime. So first let's recall how observer S will locate the coordinates of this point. So on this diagram, what you would have to do is you would have to define a unit length along the x-axis, and then you have to decide when I drop a perpendicular from this point, the spacetime point, down to the x-axis, how many unit steps do I have to go, okay, to reach this point over here? That would define the x coordinate of the spacetime point. And similarly, for the y coordinate, I would have to define a unit ct distance, and then I would drop a perpendicular from the spacetime point onto the y-axis, and then figure out how many unit intervals I need to travel, and that would tell me how many ct's I am away from the origin in time, and that would locate the time coordinate of the spacetime point. So what we need to do is something similar for the frame S prime. We need to first identify the x prime axis and the t prime axis, and then we need to drop perpendiculars onto the x prime and t prime axes, and then we need to find out how many unit distances along those x prime and t prime axes this spacetime point is away from the origin. Okay, so let's begin by first finding out the axes x prime is 0, x prime and t prime for the observers S prime. So let me just erase what we have in this diagram here. So to find, let's say, the x prime axis, let me write this down. To find the x prime axis, we just need to locate all points, all spacetime points with t prime is 0. Okay, just as for frame S, if we take all the points with t is equal to 0, we would get the full x-axis. Okay, so the points with t prime is 0 are the points where, if we just look at our equation, those are the points where ct is equal to beta times x. Okay, and what this means is this is a line which passes through the origin, and it has slope beta. Okay, and let's assume that beta is positive without loss of generality. That is, the frame S prime is moving in the positive x direction. And the other thing is, we know that the speed has to be less than 1. So beta is less than 1. So this slope beta is less than 1, which means that the angle that this line makes with the x-axis is less than 45 degrees. Okay, so it's a line which passes through the origin and has slope beta which is less than 45 degrees, okay, or between 0 and 45 degrees. So if you're slightly confused about using c times t, okay, you can just define c times t as w, and then this line that we have is simply w is the y coordinate on our graph, and x is the x coordinate, and therefore this is a line, okay, with where beta is the slope. So let's go ahead and draw that line. So let's first draw our light cone. So let's just make some more space here. And so first I'm going to draw the light cone. These are light rays which are sent out from the origin, and the paths that they would traverse in space-time. And this angle is 45 degrees. Okay, the angle that the light ray makes is 45 degrees. And now the x prime axis, okay, of observer S prime would look something like this. Okay, it would be some line which has a slope less than 45 degrees. Okay, so this would define the x prime axis. And just to be clear, yellow is our light cone. This is the future light cone, and the one below, for t negative is the past light cone. And now similarly, we can locate our t prime axis by finding all points with x prime equal to 0. Okay, so to locate t prime axis, we find all points with x prime equal to 0. And so those points would be the ones for which x is equal to beta times ct, or equivalently the points for which ct is 1 by beta times x. Okay, or in this notation where we define ct as w, w is 1 by beta times x. So this would again be a line passing through the origin. With slope 1 by beta, okay, rather than beta, which means that the angle that this line makes would be greater than 45 degrees. Okay, but still less than 90 degrees for positive values of beta. Okay, so and remember that in the previous case, tan theta was beta. Okay, in this case, the slope of the line for which t prime is 0 would be 1 by beta. So let's draw that over here. So here I've drawn the t prime is 0 axis. So if I call this angle theta and this angle theta prime, tan theta is beta, but tan theta prime is 1 by beta. So what that tells you is that theta is, or theta prime is 90 minus theta. In other words, this angle will also be theta, okay, or the slope, if I would measure the slope relative to the y-axis rather than the x-axis, would also be beta. Okay, so in other words, the x prime is 0 axis and the t prime is 0 axis, or the ct prime is 0 axis. They make equal angles, okay, with the x is equal to 0 axis with the x-axis and the ct axis. Okay, so let me just erase these extra angle labels. Okay, sorry, to be clear, this is the x prime axis, this one here, which has all points where t prime is 0, and this is the t prime axis for which all points have x prime is 0. Okay, so let me explicitly write that here. So these points have ct prime is 0, every point on this axis, and every point on this axis has x prime 0. So now that we've identified our axes for the primed observer, we need to define a unit length for the primed observers. So first, let's take our reference unit length for the x-axis. So let's imagine that for the original observer S, the unit length is over here, okay, at 1 unit along the x-axis. So now we want to know what is a unit length along the x prime axis. That unit length is not going to be the same. It's not just going to be the same distance that we have seen as measured by the S observer, okay? Because this transformation, as we've seen in these space-time diagrams, the correct thing that all observers agree on is the space-time distance between 2 points, okay? So what that means is, if I take the set of all points with the same space-time distance, the set of all points with the same space-time distance as this point here, the unit point, which we'll denote as P. Okay, the set of all space-time points with the same distance from the origin would lie on a hyperbola with asymptotes on these light cone axes. Okay, so all of these points, all of these green points on this curve are equidistant from the origin 0, 0. So what that means is all these points as described by observer 1, that is observer S, have ct square minus x square equal to 1. But this space-time interval is the same for all inertial observers, so this is also the same as ct prime square minus x prime square. So all points on this hyperbola satisfy this equation according to observers S, and they satisfy this equation here for observers S prime. Okay, so in particular, along the x prime axis, okay, which is this pink axis over here, what you would have is, since t prime is 0, this point of intersection here, which we will call p prime, would correspond to the point of x prime being 1 unit distance. Okay, so this would correspond to the point x prime is 1. So this hyperbola that we used to construct this is called a unit hyperbola, because all observers agree that that ct square minus x square is 1 in whatever t and x coordinates they are measuring. All right, so now we've located the x is equal to 1 point and the x prime is 1, t prime is 0 point, and this is the x is 1, t is 0 point. So this is a unit distance along the x-axis as measured by an observer S, and this point here, p prime, is a unit distance as measured by the S prime observer along the x-axis at t prime is equal to 0. Now on our sheet of paper, you can easily convince yourself that this length is longer, okay, than this length over here. That length measure, of course, is not a reasonable measure of distance at all, right, for any inertial observer. It's just the measure of length on our sheet of paper, okay, which happens to be in Euclidean space. So you can in fact convince yourself that the length of this line segment, okay, if this length is 1 unit, the length of this line segment over here is square root of 1 plus beta over 1 minus beta. Okay, this is not important, it's just to tell you that this length on the sheet of paper over here is actually going to be longer than this length over here. Okay, so let me just erase all the extra things that we don't need. Okay, so now we've identified a unit length along the x prime axis. Similarly, we can identify a unit length along the t prime axis. To do that, we would identify a unit length first along the ct axis. Okay, so that unit length would be here. And this length on our sheet of paper would be exactly the same as this length over here. Okay, so this would be correspond to the coordinates ct is equal to 1. And now again we do the same thing. We draw a unit hyperbola passing through this point. So that point, so this unit hyperbola would lie in the future light cone of the origin. And now we see where this unit hyperbola intersects the t prime axis. Okay, and this would define a unit length along, ct prime is equal to 1. And this would define the point where ct prime is equal to 1. And since these points lie along the t prime axis, all these points have x prime is 0. So this is again a unit length along our t prime axis. Okay, and keep in mind that again on our sheet of paper that this length would be longer, okay, than this length over here. Okay, again by a factor of square root 1 plus beta over square root of 1 minus beta. So far we have seen that the axis of coordinates as seen by the primed observer, that is the x prime axis and the t prime axis, those appear to be tilted with respect to the x and t axis, and they also appear to be squeezed, that is the x prime axis is tilted this way, but the t prime axis is not tilted this way, it's rather tilted this way. Okay, so on our sheet of paper again, these axes are, the t prime axis and the x prime axis are non-orthogonal. So it would appear on our sheet of paper that we have now gone, by making a Lorentz transformation, from an orthogonal coordinate system to a non-orthogonal coordinate system, or what is known in coordinate geometry as oblique axes. And remember again that the slope here of this line, this angle, if we call this angle theta, then tan theta is beta, and this angle is theta as well. So if we increase the speed of observer S prime relative to observers S, then the angle theta increases, and these axes get squeezed even more towards the light cone. Okay, and we've also identified unit lengths along the x-axis and the x prime axis, and similarly along the t-axis and the t prime axis, by using our unit hyperbolas. So now we're ready to ask, if we have a space-time point, which I'll show over here. So let's suppose this space-time point is P. How would we label this according to observers S, and how would we label the coordinates of this, or how would we locate the coordinates of this according to observers S prime? So for observers S, what we do is we drop a perpendicular, okay, to the x-axis. In reality, what we're really doing is drawing a line parallel to the time axis, okay, and seeing where that line intersects the x-axis. Okay, so all of these points have a fixed x. Okay, all of the points here on this perpendicular have a fixed value of x, but they have differing values of t. So when we see where this intersects the x-axis, we have located the x-coordinate, okay, of the point P, and we get the numerical value of the x-coordinate by seeing how many unit lengths we have to traverse, okay, to get to this point over here. And similarly for the time coordinate, we draw a parallel to the x-axis, since the parallel to the x-axis all have the same time coordinate. So all these points over here have the same time coordinate, and by seeing what the time coordinate is when we intersect the time axis, okay, by again measuring how many unit time intervals we have to cover to get to this point, we can also locate the time coordinate of this point. Okay, so this is how we locate the space and time coordinates of P with respect to observer S's coordinates. So now suppose we want to locate the coordinates of P according to the primed observer. So let's start by trying to find, let's say, the x prime coordinate of this point P. So now what we're doing is we're looking for the set of all points with the same x prime, let's call it x prime P, of this point, but with differing values of time. That is, we're looking for x prime P is equal to constant, that line. Okay, and you can easily convince yourself that the line x prime P is a constant will be a line which is parallel to the x prime is equal to 0 line, and therefore what we would get is a line that passes through P and that is parallel to the x prime is equal to 0 line. So let's draw that. So this is what that line would look like. Okay, this would be the x prime P is equal to constant line which passes through P and is parallel to the x prime is equal to 0 line. Okay, and what you would then do is see where this intersects the x prime axis, and now that we know what a unit measure is along the x prime axis, we can figure out how many x primes or how many unit x primes we have to travel to get to this point. So that would locate for us the value of x prime P. Remember, everywhere on this line x prime P is constant. This is just locating the value on the x prime axis. So just to be clear, we could have similarly labeled the x coordinate as xp and ctp. So in the old coordinates, the point P has coordinates ctp, comma xp. And in the new coordinates, it has coordinates ctp prime, comma xp prime. So we just discussed how to find xp prime. We draw parallel to the t prime axis, and we find out where this parallel intersects the x prime axis. And then, since all points on this line have xp prime equals constant, we just need to find out, given that we know what our unit length is along the x prime axis, we can find out what the value of xp prime is. So in this case, xp prime would be something like 1.2, given that this length over here that we've shown is x prime is equal to 1. Now similarly, we can find out the tp prime value. In this case, we would have to draw a parallel to the x prime axis passing through the point P. This would give us all points with tp or tp prime equal to constant. So let's draw that. So this line over here is a line which passes through the point P and is parallel to the x prime axis. So all points on this line have t prime is equal to constant, and so if they pass through the point P, which has coordinate ctp prime, then all points on this line have time coordinate tp prime according to the primed observers. And so now what we would have to do is see where this line intersects the t prime axis, which would be over here, and then we would have to identify how many, given the unit of ct prime is equal to 1 that we've previously identified, we have to know how many units in t prime we have traversed to get to this point. So in this case, TP prime would be something like, or CTP prime would be something like 0.8, okay, because it's only about 1/8 of the distance to the unit point along the T prime axis. So let's draw another picture of what we've learned to see how we locate the coordinates of many points using a grid. So to recap, if we go to the frame of observer S and we draw a space-time diagram with their x coordinate and their time coordinate, we could imagine drawing lines which are parallel to the x-axis or the t-axis. So the lines parallel to the x-axis have constant t values. The lines parallel to the t-axis have constant x values. So let's go ahead and draw a bunch of those lines. So if you imagine a whole grid of this form, now it's easy to locate the coordinates of any point. For example, if we want to locate the coordinates of this point over here, we just have to see which t prime line this lies on. This would locate, which t line this lies on, and this would tell us its t coordinate. That would be this line. And similarly, we have to locate its x coordinate. We would identify this line, the corresponding grid line over here, and this would tell us its x coordinate. Okay, so using some kind of virtual grid of this kind, we can figure out the coordinates of any space-time point according to the original observers in frame S. Now let's see what this looks like for an observer in frame S prime. So the first thing that we have to do is, on the same space-time diagram for observer or frame S, we draw the axes of observer S prime. And now for observers S prime, these axes are going to be tilted, or oblique axis, with respect to the original space-time axis of x and t in frame S. And the angle of tilt will be theta, where tan theta is 1 over beta, okay, where beta is the relative velocity parameter of S prime relative to S. And similarly, this angle here will be theta. And now what we have to do, if we want to locate the space-time coordinates of any point on the space-time diagram according to observers in the frame S prime, we would have to draw a similar grid, except the grid would have lines which are parallel to the t prime axis and parallel to the x prime axis. So let's draw those. So this is what that grid would look like. So these lines here are parallel to the t prime axis, and these lines here are parallel to the x prime axis. So if we want to locate, let's say, if for this particular space-time point, what is the t prime and x prime coordinate, I simply locate which grid lines this lies on. So if I want to locate its x prime coordinate, I would locate the grid line parallel to the t prime axis, see where this intersects the x prime axis, and compare it to what is a unit distance along the x prime axis. And similarly, if I want to find the t prime coordinate, I would locate which grid line this lies on, which is parallel to the x prime axis, see where that intersects the t prime axis, and see how many unit lengths along the t prime axis I have to take to get to this point. Now, I made a mistake down here. Tan theta is beta, not 1 by beta. So the interesting thing that you can see, as beta gets larger, that is, as beta goes from 0 to 1, that is the speed approach of S prime relative to S approaches the speed of light, this angle theta gets larger to the maximum limit where, as I've shown this light cone over here, these axes, the x prime axis and the t prime axis, would get squeezed closer and closer towards the light cone. And as they get squeezed, these grid lines, which are parallel to the x prime and t prime axis, would also get squeezed, okay, squeezed and stretched. So, so you can imagine the shape of this grid okay, as the speed of s prime gets closer and closer to the speed of light. Okay, the grid gets squeezed and stretched as the axes x prime and t prime get pulled closer and closer to the light cone. So now let's try to understand a few of the phenomena that we've talked about, like relativity of simultaneity, relativity of lengths, and relativity of time intervals, as seen by different observers who are in a state of relative motion with respect to each other. And we will see these phenomena once again using our tool, our new tool of spacetime diagrams. So let's start by trying to understand the relativity of simultaneity from the point of view of the spacetime diagrams. So let's consider two events which, according to an observer S, okay, where our observer S has this time axis and this x-axis. And let's consider two events which have the same time coordinate according to an observer in the frame S. So if we take these 2 points over here, these 2 points appear to have, these two space-time points, if I want to locate their time coordinate, I would draw a line passing through these points. Let's call this event 1 and event 2. I would draw a line passing through these points parallel through the x-axis to locate their time coordinates. So that line would look something like this. It passes through E1 and it's parallel to the x-axis, but the same line also passes through E2 and is parallel to the x-axis. So both these points lie on the same line of constant t. Okay, so that is both events E1 and E2 are simultaneous as seen by an observer in frame S. Are simultaneous in frame S. Now we would like to know, do observers in the frame S prime perceive them to be non-simultaneous? So to locate their time coordinates according to observers in the frame S prime, what we would need to do is we would need to draw grid lines which are parallel to the x prime axis, okay, and passing through the points E1 and E2 respectively. So we draw two different lines. So let's draw those lines. So I've drawn the lines over here. This line is parallel to the x prime axis and it passes through the point E1. This line is parallel to the x prime axis and it passes through the point E2. And now you see that these lines intersect the t prime axis at different points, which means the t prime coordinates of events E1 and E2 are not the same. Or in other words, we can say E1 and E2 are not simultaneous in frame prime. Okay. How about two events now which are simultaneous in frame S prime? So let's try to identify those. So let me erase the previous grid lines. So let's take 2 points which have the same t prime coordinate. So one way to easily do that is let's draw a line which is parallel to the x prime axis. So let me just draw that line. And all points on this line have the same t prime coordinate. So if, in particular, if we take 2 points over here, let's say here and here, then these 2 points, which we can denote as E3, event 3 and event 4, they would have the same t prime coordinate. So E3 and E4 would appear to be simultaneous. To observers in S prime. But now, what would an observer or the frame S conclude about events E3 and E4? Well, that's easy to see. What we do is, again, we draw grid lines which are parallel to the x-axis, which pass through the points E3 and E4. So here are those grid lines. And you can see that they are not the same grid line, okay, which means that they intersect the time axis of the frame S at different time points. And therefore, the points E3 and E4 do not have the same time coordinate according to observers in frame S. So E3, E4 are non-simultaneous events in the frame S. And now let's discuss length contraction from the point of view of these space-time diagrams. So before we discuss length contraction, let me just remind you how we choose our units along the x and t axis. So let's suppose these are our units, so these are equidistant. This is from 1 to 2, 2 to 3. And similarly, along the x prime axis, we have a unit distance, but that unit distance, if you remember, was constructed using the hyperbola, the unit hyperbola that passes through the point x is equal to 1, t is equal to 0. So on our Euclidean diagram, okay, this diagram which is on a paper, this length is actually longer than 1 unit, okay, that is our reference over here. But this unit of 1 refers to a length of 1 meter as seen in the frame S prime. Okay, so now let's imagine that we have a rod placed with 2 endpoints. So let's say placed over here between the endpoints 2 and 3. So let me just draw that again. So let's suppose that we have a rod placed over here. And this rod is at rest in the frame S. Okay, so if we want to measure the length of the rod in frame S, we would locate one endpoint and then the other endpoint at the same instant of time in frame S. So in this case, this is at t is equal to 0. And we would measure the length of the rod. Now, if the rod continues to remain at rest in frame S, then for all future instants of time, we would have that, so if we draw the endpoints of this rod, if it continues to remain at rest, the endpoints of this rod at a future instant of time would look like this. Okay, so the rod would continue to have a rest length of 1 unit or 1 meter. Let's assume that we're measuring x in meters. So it would continue to have this unit length throughout. Okay, and so we could draw the world line of one end of the rod and the world line of one end of the rod, which is all the space-time points that this end of the rod passes through, would look like this. Okay, it just stays at the same x coordinate, but its t coordinate changes. And similarly, if we locate the other end of the rod and we ask what its world line would look like, that world line would look like this. Okay, it would stay at the same x coordinate but have a changing t coordinate. So for any future instant of time, if we locate the endpoints of this rod, the length of the rod would always be the same. It would be 1 meter as seen in the frame S. Now what we'd like to do is understand what an observer in frame S prime would measure the length of this rod to be. So let's suppose that the observer in S prime chooses to measure one end of the rod at, let's say, this instant of time. Now, what the observer in S prime needs to do is to locate the other end of this rod at the same instant of time according to them. And remember that a simultaneous measurement, as seen in frame S, which would be to identify this time, this point in space and time of the other end of the rod, would not be a simultaneous measurement according to observers in frame S prime. So for an observer in frame S prime, they would first have to decide what time they are measuring this endpoint of the rod. And we know how to do that. Let's draw a grid line which passes through this point and is parallel to the X prime axis. So that would be this grid line over here. And now what you would do is you would say that all points on this line have the same value of t prime. That is, if the value here at this endpoint is ta prime, the value here is tb prime.